This is preparation for exercise 30.2, and we move on to talking about the activity of radioactive nuclei. So activity is basically how many nuclei are decaying every second in a source of radioactive material. And it should make some sense to you that if you have, for example, 1 kilogram of an alpha particle emitting source, and you have another sample of a 2 kilogram of mass 2 kilograms, the 2 kilogram must be emitting more alpha particles than the 1 kilogram because there's more nuclei present. So there's more of a chance of those decaying at a greater rate. And that's essentially the law of radioactive decay. Now, in your maths tables, there are, basically this is the formula you worry about here. These two formulas here, I should say. The first one is kind of hinting at the law of radioactive decay. No. So let's go through what these stand for. So A means activity. It's the number of disintegrations per second, and the symbol for it is A. It's measured in becquerels, and this is important here. Recognizing what is actually A in the question. And it can be referred to in a number of ways. It can be referred to simply as the number of disintegrations per second, the decay rate, the number of alpha particles emitted per second, the number of beta particles emitted per second. They all mean A, activity. Now then we have N is the number of atomic nuclei, the number of nuclei present in a sample, and then lambda relates A to N. It's called the decay constant. And again, it'll just be called that in a question. Then T1/2 is the half-life, the time taken for half of the radioactive nuclei to decay. Because the decay radioactivity is an entirely random process, you can never say for sure when exactly the last nuclei will decay, but you can say to a fair degree of accuracy, you can give the time for half it to decay. So on a graph like this, activity against time, all you do is go down to halfway from the activity at the start, go to halfway down, draw a line across and a line down, and that will give you the half-life. Now the half-life is measured in seconds. Make sure you convert to seconds in a question. Sometimes it's given in minutes and hours, and you'll mess up the question if you don't. Now, one other small bit of mathsy stuff here. So, just one other small thing here. So, half-life radioactive isotope is 30 minutes. How many half-lives in 4 hours? Well, there's 8 30 minutes in 4 hours, so that's 8 half-lives. What fraction remains undecayed after 1.5 hours? Well, if you look here, after 30 minutes, this much will be decayed. After a further 30 minutes, this much will be decayed. And after a further 30 minutes, that's your 3 half-lives, 1.5 hours. That much will be decayed. That means 1/8 remains. And there's actually a formula for that. 1/2 to the power of n. So there's 3 half-lives in 1.5 hours, so 1/2 cubed is 8. And you can work out the last question using that information there as well. As an example from the exercise, this is N. This second number here is the activity. From that you can work out the decay constant because A is equal to lambda N from your maths tables. Work it out there, and then you can go on to work out T1/2. T1/2 is equal to the natural log of 2 over lambda. So put those numbers in there, and you can see here the half-life of this particular question is huge. Some particles might take billions of years to decay, and that's the reason why sometimes the answers can be very big. And then just back over to your book for a second. So would you please go and try exercise 30.2. Thank you.